He focuses on physics-guided machine learning for aerospace manufacturing and closed-loop manufacturing utilizing digital twin technologies. He has extensive experience as a researcher and published author. Dr. Wang's works have been published in the SERP Annals, the International Journal of Machine Tools and Manufacture, and the International Journal of Advanced Manufacturing Technology that include a hybrid cutting force model for machining of titanium alloys, high-speed milling of titanium alloys using binderless CBN tools, and study on orthogonal turning of titanium alloys with different coolant supply strategies. Dr. Wang earned his PhD from the National University of Singapore and also holds a master's degree from the Zhigang University of Aeronautics and Astronautics in China. I'd like to call up Dr. Zhigang Wang to deliver his presentation today.
Good morning, everyone. So thanks, Monsieur, for your introduction. So here I'm going to talk about what we have done in terms of this called the physics-based digital twin. So mainly we are focused on the CNC machining since because of the nature of our work. So this first chart shows some background why it's needed for this study. So the left-hand side shows the typical, this is the product life cycle of the traditional manufacturing process. Let's say start from design to process planning and to production engineering to final manufacturing, and after that would be the surface. So in this cycle, there are lots of data actually started from the design, from like a tolerance, detailed geometries, and also during this process planning. So let's say inside the CAM software, there are lots of data there, such as the detailed tool geometries, and then the final tolerance you want to achieve, and also the surface quality you want to achieve. But after that, down to the factory floor. So typically the operators only have the CNC program there uploaded to the machine, and also together with some kind of a tooling data from the tool management device. They don't have too much kind of upstream information from the design to the process planning. So here we try to bring the gap. Let's say, so why not let's flow down the data from design and process planning to downstream manufacturing. So use that kind of information as a digital twin or a reference to monitor the actual machining process, try to achieve the higher reliability. So the right-hand side is just some kind of a survey data about why it is important to do that, such as, so this is kind of like a 30% of the operation cost sometimes comes from the maintenance. And also overall, like, globally, they spend about $50 billion each year just to try to maintain the manufacturing equipment. So it's basically it's a big deal to do this. It's a lot of cost reduction there. So this is the slide that shows some internal results. So basically, RTX previously we also called it the UTC. So we did some kind of a supply health assessment, try to look at all the manufacturing facilities, how they perform basically, internal and external. So overall, you can see from here, so only 6% of those suppliers, they are doing well basically. The others, there are still some kind of a room to improvement. Specifically, let's say for this, almost 1/3 of them, there are still lots of room to improve their productivity and process reliability. So previously, George and Fahad, they already talk about like the technologies are now available, such as the sensors, and then the analytics. So here, so many I just try to highlight. So there are lots of kind of hardware and software and algorithms available right now. So this is the right time to do this kind of digital twin for the process monitoring and control, I mean, in real time. So here is a kind of details about, so let's say this is the typical CNC machine structure. So it has a 5-axis machine, it has a rotary table, and with a 3 linear axis drive there. So lots of sensors there already inside the machine. And also, in order to drive these machines, you have like a linear encoder there. So all the signals are there, basically. The thing is how to use it, how to have this context information in the factory flow so that you can turn this data into information and into knowledge, and then use that knowledge to control this process to achieve the higher productivity. So here, the first thing we did is like we look at so what is the kind of a data structure flow on this CNC machine? So as you can see from the left-hand side, so the machine tool typically driven by the pneumatic controller, and for the pneumatic controller, it also controls the servo motor, and then spinner motor, and then precision encoders. And also together with that, there are some other data, such as the tooling information, and also the embedded sensor information, and also for the external PLC data there. So lots of data there. And then it organized with like the position and motor current signal there, and also like for the CNC program. So basically it's organized as like the motion by motion. And if you carefully break it down, you can divide it into different kind of events or states based on the actual machine, what it's doing. So with this kind of information, like such as event at a state of this specific machine at a specific time, and then we try to organize the data to follow this kind of format. So basically break down to state, event, and for each kind of variable, we associate it with different data, such as the position, and then the motor current together with external certain sensor data there. And with that, so you can kind of, with that kind of a context information, you can perform the real-time control. So here shows, so the physics-based model. So how we can integrate that one to follow the CNC structured data format to organize the data. So here we have the input, such as the material, tooling data, and also you have the NC program and a machine model and a control model. And based on the simulation with this NC program here, so basically based on the tool and the material contact information, so you can calculate the cutting forces. And thereafter, you can calculate how much forces, I mean, each drive axis need to drive the axis to achieve that motion together with the spindle power consumption, and then the load applied on the spindle. And eventually we can also calculate like the diffraction applied on the workpiece side, and also can optimize the program. Since you have the node there, you know the capacity of the spindle and the tool can take. So sometimes you can speed up, or sometimes you can slow down, depends on the user's objective. And eventually we can generate the digital twin. So which is yes. Which one? This one? Oh, this is diffraction. Okay, thanks. So the digital twin means this is the process digital twin. So it kind of mimics how the machine will behave in the actual time. So with that, we can use that as a reference to do the real-time process control and monitoring. So this slide just shows how it works. So the left-hand side is kind of called the digital domain. So how we created this digital twin started from the design, then based on the input information such as the NC program, work material, tooling data, and then together with the machine model, we can simulate how the machine will behave during the actual cutting. So after this is the kind of iterative process. So after prove out the program, then uploaded to the CNC machine to do the actual machining. And since we have this process digital twin here, so basically this is kind of more or less like break down details, state, events, and associated with all those parameters. Then later we can, based on the measurement data from the CNC, so we can compare real time together with the context information to react. Such as if you observed some abnormal condition, you either can slow down or speed up, basically. And here shows the typical use case. So here we selected like the aerostructure component part here. It needs 2 setups with 2 machines. So we break it down to different kind of a machine sequence for each operation on each machine. And then simulate the details, how the machine will behave for each kind of a sequence or each motion step. So we can break down that. And here is the video shows how it works basically. So this is more or less like the digital model of how the machine will behave during this cutting. So background. So we use our physics-based model to predict. So per motion step, once the tool moves, once it contacts with the workpiece, we simulate what's the forces applied on the tool side and also on the machine side. And also can predict the spindle load and the power consumption. And then, as George and Fahad talked about already, so I don't want to repeat this kind of algorithm here. So basically, there are lots of data there. You need some kind of algorithm to process it, to extract the useful feature and information from the data. So this plot just shows, so basically, this is all simulated results. So we have the baseline and together with like a 60. So the simulation captures like the tool wear during this operation together with some kind of uncertainties such as a vibration. So we plot this and then process it and build the baseline or the process digital twin as a reference so that, so for the downstream, so let's say if we already have the data for the 60 parts and then at this specific moment, so we observed this kind of abnormal condition in comparison to the processor digital twin, then if this condition lasts for a certain amount of time, then it will kind of alarm out, aware the operator. So maybe this is the kind of abnormal condition here. So here is a summary. So basically, we use the physics-based model by considering the material removal together with this machine tool and its controller, then build the process digital twin and use that for the real-time process monitoring and control. And also we leverage, let's say, by collaboration with UConn and CCAT to get this machine learning algorithm to extract or to process the data, to get this clean data and extract the useful information for the monitoring and control. Okay, thank you for your attention. So any questions? Yep.
I think the eventual goal is to do the thing real time. Like, am I right? First of all, like you want to do the digital twin, do that simulation very fast, so you can be able to adjust or change let's say the tool for the next experiment. So how fast is your simulation?
So yeah, good question. So this really depends on the hardware, depends on the communication between the PC and the controller. So as far as I know, so typically if let's say for the financial controller, it allows like a 1K sampling rate, the
Oh.
date. And then of course you need to take the time to process the data. Those are just the raw data, right?
Yes.
And then to react. So I would say, let's say maybe at like 0.01 seconds for one cycle, maybe. Taking the data, process it, and then send it back. Let's say if you want to override the spindle node or the feeder rate, so it takes about that time frame, 0.01 at least, to finish one cycle. This is the current hardware platform. If in future, let's say if the controller has a more powerful kind of communication devices, such as use 5G, as you mentioned in your presentation, to send this data, I mean, large amount of data faster, then we can improve maybe to do like maybe 1 millisecond maybe per cycle. So
I see.
that's kind of based on my knowledge. Okay.
Great.